Today, we're going to dive into something pretty cool for decoding the hidden patterns all around us, the hidden Markov model. Believe me, it's this amazing key that can unlock secrets everywhere, from how your phone understands you to how the stock market behaves. Okay, so let's kick things off with a little puzzle. Imagine this. You're stuck in a room with no windows for 3 days straight. But every day, someone slips you a note telling you how many ice creams were sold outside. Just from that number, could you figure out what the weather was? Hot or cold on each of those days? And that little game right there is the core of what we're talking about today. We can see the effect, the number of ice creams sold. That's easy. But the cause, the actual weather, is totally hidden from us. So how do we make a really smart guess about what we can't see based only on what we can? Well, the answer to that puzzle lies in a tool called a hidden Markov model, or as you'll hear it, an HMM. It's basically a mathematical framework built for these exact kinds of situations, where we have to connect the dots between what's visible and what's really going on behind the scenes. So at its heart, an HMM has two simple layers. You've got the hidden state. That's the thing we want to know but can't see, like whether it's hot or cold. And then you have the visible observation. That's the data this hidden state produces, the stuff we can see, like 1, 2, or 3 ice creams being sold. And this isn't just some abstract idea with ice cream. This is real stuff. HMMs are the powerhouse behind tech you use, like every single day. When your phone turns your voice into text, that's an HMM figuring out the words you probably said, the hidden state, from the raw sound waves it hears. And it's the same fundamental logic for spotting trends in finance, tracking your run, or even analyzing DNA. All right, so now that we've got the basic idea of the model, we can actually use it to answer two really big questions. The first one, it's all about probability. Basically, what are the odds? Now, in the lingo, this is called likelihood computation. But what does that really mean? It means we have our model, we know the chances of it being hot or cold, and we know how many ice creams people tend to buy in each weather. So the question becomes, based on those rules, what was the actual specific probability of seeing the data we actually saw? For example, let's say we observed sales of 3 ice creams, then 1, then 3 again. The question we're asking is, what's the total probability of that exact sequence happening? Not just any sequence, but that specific one, 3, 1, 3. Now, your first instinct might be to just brute force it, right? You could literally list out every single possible weather pattern for 3 days. Hot, 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 cold, and so on. Then you'd calculate the probability of each one of those paths giving you that 3-1-3 ice cream result, and then you just add them all up. But you can already see where this is going, can't you? For 3 days, that's only 8 paths. But what if we had data for a whole year? The number of paths would be, well, it would be a ridiculously huge number that no computer could ever crunch through. It's just impossible. There's gotta be a smarter way, right? And of course there is. It's called the forward algorithm. And it's so much smarter. Instead of trying to calculate every single path from the beginning, it works 1 day at a time. It figures out the probabilities for day 1. Then it uses those results to build day 2. And the day 2 results to build day 3. It's so efficient because it keeps reusing its own work, which completely avoids that insane computational explosion. But wait a minute. Knowing the odds of seeing our data, that's only one piece of the puzzle. Now we want to do something even more interesting. We want to uncover the most likely hidden story that caused that data in the first place. So the whole goal changes. We're not asking, what are the chances of seeing 313 anymore? Now we're asking, out of all those possible weather paths, hot, cold, hot, all of them, which single one is the most probable explanation for what we saw? We're looking for the best story. And to do that, we need a totally different tool. See, the forward algorithm we just talked about, that was a sum problem. It was adding up the probabilities of all the possible paths to get a total. But to find the best story, we need to solve a max problem. We need to find the one path with the maximum probability. And for that, we bring in the Viterbi algorithm. The way the Viterbi algorithm works is it's so elegant. It also moves forward 1 day at a time, but with one huge difference. At each step, instead of keeping track of all the possibilities, It only remembers the single most likely path that could have gotten it to that point. It's like a super efficient detective who, at every fork in the road, only follows the most promising trail and just ignores all the dead ends. Okay, so let's take a step back for a second. We've tackled likelihood, we've tackled decoding, we've used this ice cream puzzle, but why does any of this really matter? Why is this so important? All right, so what's the big picture here? What should you remember? First, HMMs are a bridge from the seen to the unseen. They give us a real mathematical way to connect those two worlds. Second, they're designed for sequences of events, things that happen over time. And most importantly, they help us answer those two key questions: what are the odds and what's the best story, using brilliant, efficient algorithms that make them a cornerstone of modern AI. And that really leaves us with this one big, fascinating thought. From the weather outside to the words we speak, HMMs help us find the hidden structure in a world that can often feel random. It just makes you wonder, what other invisible patterns, what other hidden causes are all around us, just waiting for the right algorithm to bring them into the light?